does cos look like? What does tan look like? So we've had these formulas since grade 10, the SOHCAHTOA formulas, and you know how to use them and how to solve, but what do they look like graphically? You know what a line looks like. Show me a line using your hands or your arms. Show me a parabola. Show me a square root graph. Show me a cubic. This will be fun. So you know what all those graphs look like. All we're doing today is we're going to look at what does sine and cos look like. These are super fun graphs. You'll notice, first of all, it's got a really long x-axis and a fairly short y-axis. So this isn't a standard 10 to negative 10 kind of graph. The reason that is because the largest value I need is 1 and negative 1. Tell me why. Because that's the unit circle, right? Sine and cos can't be bigger than 1. That's why I didn't need a really long y-axis. Now, instead of putting 1, 2, 3, 4, etc. on the x-axis, I'm going to use really good unit circle values. I'm going to start at 0. And the next one I'm going to use is pi on 2. Why am I choosing to use pi on 2?
Because you hate degrees.
I do, yes. But why pi on 2? Because that's 9 degrees. That's the top of the circle. What's the next unit you think I'm going to use?
180.
Which is pi. And then 3 pi on 2. And then 2 pi. What's the sine value at 0? So what's the y-coordinate when there is no angle on the unit circle? 0. Pi on 2, top of the circle, what's the sine value? 1. Pi, so left-hand side of the circle, what's the y value?
0. Negative 0.
3 pi on 2, the bottom of the circle. And all the way back around to 2 pi. Look how cool that graph is. Where are my physics people? Does that look familiar?
Yes.
Yeah, where have you seen that kind of function before? Light waves, sound waves, any kind of waves. They're all called sinusoidal functions, which we'll talk about tomorrow. What this is one revolution of the circle. So if you were to go around the unit circle with sine, you'd start at 0, you'd go up to 1, you'd come back to 0, you'd go down to negative 1, you'd go at 0. Oh, no, I am, I'm good. Oh, we're good. Why the arrow at the end? Keeps going on forever. And I could do the negative side too, I just chose not to. Domain. Domain. X element of the reals, except I don't have an x, I have theta element of the reals. The range, so it's a unit circle. What's the lowest y value and what's the highest y value?
Negative 1 is less than or equal to theta is less than or equal to y.
Kind of, but because it's a range, I don't want theta in there, I want y. Because the range always is all the possible y values.
And the domain is all the possible x values.
Which we don't have x, we have theta. Remember, not feta like the cheese. I'm going to switch colors because I'm going to do cos on the same set of axes. Okay, right-hand side of the circle, 0, what's the cos value? 1. Pi on 2, top of the circle, what's the cos value? Left-hand side of the circle, pi, what's the cos value?
Negative 1.
3 pi on 2, the bottom of the circle.
Negative 0.
And all the way back around to 2 pi. Check out cos. What's the relationship between sine and cos? It's not flipped. Think of everything you know about transformations. What's the relationship between sine and cos? It's just a translation. What direction have I translated it? To the left. I've just moved this over. Sine and cos is just a translation. That's it. Yes, sir.
They also have the meeting plane.
They do. They have intersection points, which we'll talk about in a second. Domain of cos?
Theta ER.
The range of cos? What do you notice about the two domain and ranges? Okay, they have intersection points here, and they have intersection points here. And this one happens to be halfway between 0 and pi on 2. What's halfway between 0 and pi on 2?
45 degrees.
And what would that be in rads? Why does that make sense the graphs cross at pi on 4? Well, what's the sine value at pi on 4? Root 2 on 2. And what's the cos value at pi on 4? That's why they cross there. This is your pi on 4.
Or if you prefer in degrees, 45.
They also cross here, which is in between pi and 3 pi on 2. Well, where else are the two coordinates the same? So they're same in quadrant 1. Are they the same in quadrant 2? No, because cos is negative, sine is positive. What about quadrant 3?
Yes.
So this is our 5 pi on 4.
Or 135.
Yes. Isn't that kind of cool? Look, there's the unit circle. Okay, let's graph tan. He's going to get his own set of axes because I don't want to mix them up with cos and sine.
Why? With as many different colors as you have, you could.
Oh, but you're going to see he's a completely different graph. He's special.
Oh boy.
Yeah, he's special. Tan is special. Yeah, he's special. He's that special sibling. We all have one. Well, I guess only children don't. So we don't all have one. Okay, same thing. Let's think of our 5 values of tan. What's the tan at the right side of the circle? So tan of 0.
Negative 0.
Tan of pi on 2. Ooh, undefined. How do I show something that's undefined?
You don't.
We do. Think back to last year. Rational graphs are non-permissible values. How did we graph them? Asymptotes. Remember those guys? It's called an asymptote. It's the thing that the lines can't cross. It can come really, really, really close, but it can't actually touch it. Yeah, it's undefined.
Another big word.
Asymptote. There's a shirt that some people have that says, "Kiss my asymptote." Pi, left-hand side of the circle. What's the tan value at pi?
0.
0. Bottom of the circle, 3 pi on 2. Undefined, so we're going to have another asymptote. See, this is why tan is special. There's some funky stuff going on. What about 2 pi? So back to where 0 is. 0. Okay, well that didn't really give us a lot. So what I'm going to do is I'm going to add in the halfway points between these points. So I'm just putting a tick halfway between 0 and pi on 2, halfway between pi on 2 and pi, et cetera, et cetera. And we already talked above, this is the pi on 4 family. So halfway of pi on 2 has to be pi on 4. And in quadrant 2, what's the pi on 4 family? 3 pi on 4. And in quadrant 3, 5 pi on 4. And quadrant 4, 7 pi on 4. And I'm choosing the pi on 4 family, number 1, because the tan values are easy to plot, number 2, because it's halfway in between. Okay, so what's the tan of the pi on 4 family? Okay, so in quadrant 1, it's going to be positive 1. Quadrant 2, negative 1. Quadrant 3, positive 1. And quadrant 4, no. Check out tan. There's what it looks like in quadrant 1. Okay, comes from the origin, passes through that point, approaches the asymptote, but never actually touches it.
Because it can't, that's illegal.
Because it can't, it's illegal, the paper would blow up. Take a look at the middle section. It's going to approach the asymptote on the left, cross through these points, and approach the asymptote on the right. And in quadrant 4, it's going to copy what it did in quadrant 2. There is funky tan. That's why I didn't want to put it on the same set of axes, because he's kind of crazy. I didn't put one, but I could. Grab your calcs, and if you don't have, just peek over someone's shoulder. Let's just graph these on the calc so you can see what they look like. Can you see my calc? Can you see it there, or is it too dark? It's okay. First thing I want you to do is check your mode. What should we be in? Rads. Make sure radians is black, degrees is white, and then just clear out of there. Go into your y equals. If you've got any functions, clear them out. I'm going to put sine x into y1. And then I'm going to jump down and put cos x into y2. No, tan we're going to do separately because, again, he looks so different. I just want to compare first sine to cos. Now we go to zoom, but now we're not going to pick zoom standard because that's not going to do it for a trig graph. Which of these do you think might be for a trig graph?
Well, yes, zoom square.
There he is. And so when we did in Unit 1 solving these equations graphically, that's why they had those bumps to them. Okay, let's go back into our y equals, clear it out, and we'll put tan x into y1. And we'll zoom trig. How funky is that? Now the graph has trouble with asymptotes. They can't do them as dotted line because it's impossible to get pixels that are right vertical with each other, so they'll kind of do it as solid lines. Occasionally the asymptotes will just not appear, so sometimes you might just have those swoops, but you just need to know roughly this is what a tan graph looks like.
I've got one of the newer calculators and it just doesn't put any.
Yeah, sometimes they just, calculator is a hard time with vertical lines, but there's what it looks like. Questions so far? Kind of cool now you can picture sine, cos, and tan. Before they were just these magical formulas that you use. Now they have a picture to them. Well, guess what we're going to do with them? We're going to do transformations. We can stretch them. We can reflect them. We can translate them. You should see Michaela's face there. Just looks so sad. So sad. So I just want you to make a change. I put a typo here. That shouldn't be translations. It should be stretches, compressions, because we're going to do them first. Stretches, compressions. I'm going to talk to the coordinate people first, because I think they're going to like these graphs. If you're not a coordinate person, just wait for me. Way at the top, and I'm going to color code to the graphs I had before. I just want you to look at sine first and tell me what are the y coordinates in order. Purple was sine. So it's 0, followed by, followed by, followed by, followed by 0. And let's do the same thing, the y values for cos in order. The first y value is followed by. I love how he said that right through a yawn. Okay, just put that in your head, and I'm going to use that in a second. Y equals 2 sine theta. Is 2 outside the brackets or inside the brackets? Is it out in front or tucked inside the function? It's out in front, so that makes it vertical. Is it a multiplication or an addition subtraction? Multiplication, that makes it a stretch or compression. Is it a whole number or a fraction? That makes it a vertical stretch. X, y goes to? X to y. So for the coordinate people, you just need to take that pattern we just talked about, which for sine is 0, 1, 0, minus 1, 0. And all you need to do is multiply it by 2. What's 2 times 0? What's 1 times 2? What's 0 times 2? What's negative 1 times 2? And what's 0 times 2? If you're not a coordinate person, just come here with me. So the first point is 0. Pi on 2 would have been 1, but we're timesing 1 by 2, so it's going up to 2. The next point is 0. The next point would have been negative 1, but we're timesing by 2, so it's going to go down to negative 2. And the last point is 0. There's our first transformation of a trig graph. Is it any different than a parabola or a cubic or a square root or an absolute value or a line? Exactly the same thing, we just have a different base graph now at sine. Questions over? How about reflections? Negative 3 cos theta. So I'm going to do a reflection and a stretch in this one. The negative, outside brackets or inside brackets? That makes it vertical. Because it's a negative, it's a reflection. xy goes to? The 3, outside brackets or inside brackets? So that's vertical. Is it a multiplication or an addition subtraction? Is it a whole number or a fraction? So it is a vertical stretch. xy goes to x, 3y. All I'm going to do is grab that pattern for cos, so I'm just looking at the y coordinates. Cos starts at 1, goes to 0, minus 1, 0, 1. Then I'm going to do my vertical reflection, which just says I times these by a negative. So 1's going to become 0,
Negative 0.
negative 1, 0,
Negative 0.
and 1. Now I'm just going to take those values and do my vertical stretch, and we said we're multiplying by 3. So negative 1 goes to 0, 1, 0, and negative 1. Do you hear music too? Okay, just checking. So now my first point isn't 0, it goes down to negative 3. My pi on 2 is going to stay at 0. Pi is going to go up to 3. Pi on 2 stays at 0. And 2 pi goes down to negative 3. Aren't those easy after doing all those other transformations? Notice the curvy, kind of swoopy shape to this graph. It has to have that kind of curve. This is not a sine graph. Don't draw that on yours. That I call connect the dots. That's not a sine graph. Sine graph has curve and swoop to it. It's not straight lines like a mountain. Two definitions you need to know. The first is the height of the trig graph between a max and a min is called the amplitude. Physics people, you should know that word. This, for example, is the amplitude of the graph. Non-physics people, have you heard of an amp that's attached to a guitar? What does an amp do? It makes the sound louder, it amplifies the sound. That's because it's taking the sound wave and pulling it up vertically. That's what it has to do with it. The width of one cycle of the graph. This would be from max to max, or from min to min. Doesn't matter. I just chose to go from the bottom of the graph to the bottom of the graph. It's called the period of the graph.
Where did you get these words from?
I just stole them from other mathematicians.
Where did other mathematicians get these words from?
Probably a physicist came up with amplitude is my guess. Well, I don't know. These are going to come back tomorrow and the day after, so just keep those graphs idea in your head. Amplitude is the height of the graph. The width is called the period. Let's do some translations, because why not? Two, inside brackets or outside brackets? Multiplication or addition, subtraction? Whole number or fraction? Vertical, xy goes to? The 4, outside brackets or inside brackets? So it is vertical, it's an addition, so it is a translation, 4 units, up. I'm going to do it without the coordinates this time for the non-coordinate people. If you like the coordinates, write out that pattern, times them by 2, and then move them up. So if you're not a coordinate person, what you're going to start with is the base graph. And the base graph is just the regular coast graph. And coast graph starts at 1, goes to 0, goes to -1, goes to 0, goes to 1. So that's the equivalent to writing out the coordinates for the non-coordinate people. That's called the base graph. Yep, just coasts. What do I do first, the stretch or the translation? Why? Because it's first. And if you go back to BEDMAS, what comes first? Multiplication or addition, subtraction? Multiplication. That's why we do it first. So I'm going to take all these y values and times by 2. So 1 times 2? 2. 0 times 2? -1 times 2? 0 times 2? And 1 times 2? Bless you. My last graph is going to be in red, so grab your red pens as well. I'm going to take all these points and I'm going to count 4 units up. 1, 2, don't have enough space. If that really bothers you, put the point up here somewhere. Okay, it's going to be off the graph. The second one, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Off the graph somewhere. So all we're going to see is this little swoop down. I'm just putting the dotted line to show the points that are off the graph in case that bothers you. Is that any different than how we did parabolas? Cubics, radicals, absolute values.
It's not connected dots, right?
It's not going to have that swoopy to it. Domain of the last graph. Well, remember, even though we can only see this part, we know it goes on forever to negative infinity and forever to positive infinity because we can do 1,000 rotations of the unit circle. We could do 1,000,000 rotations of the unit circle. We could do an infinite amount of rotations of the unit circle. What is the domain going to be? Watch your variable over here. Watch your variable. Theta ER. The range is never to infinity because there's always a max and there's always a min. So the min is easy to see because it's on the graph. What is it going to be? The max, well, you would have counted up. If this was at 2 and we counted up 4, it would be at, so 2 less than equal to y less than equal to 6. Show me your thumb so far. Getting it, kind of getting it, not getting it. Put it really high so I can say it. Good, good. What the heck is this? What is that? Yes, scary numbers. Well, you need to think in terms of our coast graph, and you're never going to see a number like 2 for a horizontal translation, or 7, or -1. Why would you see a value of pi? Well, look at the x-axis. What have we broken the units into? Pies. So this is the equivalent of pi units. So it's kind of 2 units, or because of this graph, it's the 6 of these little boxes. That's all it means. It just means pi units to the. So this is our horizontal translation, pi units to the right. So 6 of these little ticks. If we didn't have all these ticks, it would be like 2 ticks of a regular graph. What's the -1? Vertical translation, 1 down. Base graph, just like before, take away all the transformations, what's left? Cos. Go ahead and draw me the base graph of cos. I'm going to do the coordinates for the coordinate people. If you're not a coordinate person, just wait a second, I will get to you. On the base graph, the first point is 0, 1. The next point is pi on 2, 0. The third point, pi, negative 1. The fourth point, 3 pi on 2, bottom of the circle, and 0. And the last point, 2 pi and 0. Transformation says that we're adding pi to the x-coordinate, and oh, it's 1, thank you. And we're subtracting 1 from the y-coordinate. Okay, we're adding pi to the x, we're subtracting 1 from the y. So this point is now going to go to, well, 0 plus pi, and 1 minus 1, 0. A half pi, or pi on 2, plus a full pi. 3 pi on 2, so pi and a half. And 0 minus 1, negative 1. Pi negative 1 is going to go to, well, pi plus pi, 2 pi, minus 1 minus 1, negative 2. I don't care about these points. Why?
Because 2 pi is the furthest at this graph.
Because they're going to be off the graph. It's going to be past 2 pi, so I'm not going to worry about them till I get there. So if you're a coordinate person, you plot these. If you're a counter, come over here with me. So this first point, I need to move all the way over to pi, and I need to drop him 1. So I moved him all the way to pi, dropped him 1. Pi on 2, I need to move all the way to 3 pi on 2, and I need to drop him 1. So pi on 2 went to 3 pi on 2, and I dropped him by 1. This original point at pi goes all the way to 2 pi and drops by 1.
What about like the rest of the graph west of?
You're always like one step ahead of me. I love it. Problem with this is you can't have an empty part of the graph like that, because we know the unit circle goes on forever and ever. So I got to figure out what would the rest of this graph look like. What would the rest of the graph? Well, if this is the max, because that's the highest point, and this is the min, what would have happened over here? Would it have gone up or would it have gone down? It had to go down because this is the max. So just by using the symmetry, what do you think is going to happen at pi at 2? It's going to be negative 1. And what do you think happened at 0? It's going to be negative 2. So we're just using that we know the graph is symmetric to fill it in. Okay, can't leave an open spot on a graph like that. So we did stretches, compressions, we did reflections, we did translations. What have we not done yet? Inverses. Oh, was there domain on range? There was domain and range. I got too excited for the inverses.
I've got 955 as well, so I'll probably have to save the inverses for this afternoon.
We probably will. That makes me a little excited, actually, that we get to hang. Domain. The range, lowest value to highest value.
-2 is equal to or greater than y, which is less equal to or greater than 0. Less than
2 to 0.
words.
Do we want to do an inverse, or we want to wait till this afternoon?
Yeah, there's not
But then, like, you'll be anxious all morning. Like, you'll be so excited. You won't be able to concentrate in your other classes.